Functions, Chapter 2, Section 1. So first we're going to start talking about relations. Relations are a correspondence between two sets. If X and Y are two elements, one from each of these sets, and if a relation exists between X and Y, then we say that X corresponds to Y or that Y depends on X, and we write X implies Y, or X arrow Y. So it's saying that you have two different groups of information. Each piece of information in the first group relates to a piece of information in the second group. Here are a couple examples of relations. On the left-hand side, we have people's names. First name and last name. The first name relates to the last name. Frank LaValle, Aaron Johnson, Mark Smith, Gregory Jones, Thomas Anderson, Michael Johnson. So the two pieces of information are tied together. Frank LaValle, the first name and the last name. So therefore there's a relation between the first name and the last name. Frank Johnson is not a part of this list. Aaron Jones is not a part of this list, but Mark Smith is. There's a relation between the first name Mark and the last name Smith. On the right-hand side, we see heights and weights. Someone who's 64 inches tall weighs 118 pounds. 71 inches tall, 194 pounds. So the heights relate to the weights and the weights relate to the heights. So that's what a relation is it's just tying two bits of information together. So you have two different sets of information and each element in the one set relates to an element in the other set. Mapping relations is where we show how those inputs, X, and outputs, Y, so the pieces of each of the sets, relate to one another. So if we're going to map this relation of X and Y, first we're going to give ourselves two bubbles to work with, and then we're going to list all of the X values, the inputs in the first bubble, and I put them in numerical order, 1, 3, 4, 6, 7, 8. And we're going to list all of the outputs in the other bubble, again in numerical order, 2, 3, 5, 6, 7, and 9. Then what we're going to do is we're going to look at each of these X and Y values, and we're going to connect them with an arrow. So when X is equal to 8, Y is equal to 5. X is equal to 3, Y is equal to 3. 4 goes to 7, 1 goes to 6, 7 goes to 2, 4 goes to 3, 6 goes to 9. And now we see a mapping, and we can use that to see what happens. If we have a 3 as our input, X, then we know that the output is going to be 3. If we have a 4 as our input, X, then it could either lead us to an output of 3 or an output of 7. So that's mapping a relation. We can also give relations using ordered pairs. So the same set of information, but now we're going to use ordered pairs, which is just putting the X value, comma, Y value inside parentheses. And this is what you're used to using when you graph two variable data. So 8 for X, Y for 5 and equal to 5 gives us 8 comma 5 or 8 5. We end up with 3 3, 4 7, 1 6, 7 2, 4 3, 6 9. So that's a listing of ordered pairs, and that would allow us to plot these points on a graph. The domain and range of relation. The domain is the set of all inputs, and the range is the set of all outputs. So since we've been dealing with X and Y, the domain would be all the possible X values. The range would be all the possible Y values. So looking at that same set, we can say that the domain is the set of numbers 1, 3, 4, 6, 7, and 8. The range is the set of numbers 2, 3, 5, 6, 7, and 9. A function, let X and Y be two non-empty sets. Okay, so they've got to have something in them. A function from x into y is a relation that associates with each element of x exactly one element of y. Well, that's a lot of words, but basically what that's saying is that a function is a special type of relation. In a function, any input can only have one output. If you tell me the x value, the input, I can tell you with 100% surety what the output value is y, because there's only one possible output. If you have an input that can go to two possible outputs, then you do not have a function, you just have a relation. So let's determine whether we have a function or not. Looking again at that relation that we've seen with x and y, we can look at that mapping that we did. It makes it very visual, and we see we're okay when x is equal to 1. When x is equal to 1, the only possibility is that y is equal to 6. So that's okay. When x is equal to 3, y has to be 3. But when x is equal to 4, y could be either 3 or 7. So there's where we got a problem, because a function can only have one output for any given input. And here we have two possible outputs for one input. So therefore, it's not a function. Well, let's look at this set of ordered pairs. We've got 1782, 3167, 6571, 2267, etc. If we look at the inputs, we actually look pretty good here. We got 17, 31, 65, 22, 80, 59, 42, 93. There's no repeated input. Since there's no repeated input, we never have the problem of having one input lead to two different outputs. So therefore, each input has only one output. We do run into a thing here that we have two 67s for outputs. We do have two 12s for outputs. So some outputs have more than one input, but that's okay, because for a function, all we need to know is that each input has only one output. And in this case, that is the case. Therefore, it is a function. Let's look at y is equal to 3x plus 2. Well, we should recognize that form. That's y equals mx plus b. That's the equation for a line. So as long as this is not a vertical line, which would be x equal to some value, then this could be a function, because if we have a line and we don't have a horizontal line, we don't have a vertical line, then every input has its own output. Each x value has its own y value. So this is a line with a slope of 3, which means it's not a vertical line. Therefore, it is a function. Each x value has its own distinct y value. What about x squared minus y squared is equal to 5? Well, here we notice that y is squared. A positive or negative value of y can be achieved from the same x value. If y is equal to 3, then y squared is 9. If y is equal to negative 3, y squared is equal to 9. So in this particular case, an input x could yield two different outputs y, thus it is not a function. Value of a function. When we're talking about functions, we tend to write them, the function f, and then in parentheses, the input of that function, in this case, x. And we read that f of x, and that's how you will hear me say it a lot, f at x, or the value of f at the number x. So if we have a function y equals f of x, x would be considered the independent variable, the input, right? It's independent of anything else. I can put any value I want in for x. And when I do that, y becomes the output. It is the dependent variable. Depending on what variable I put in for x, we will get a certain output y. Finding values of a function. F of x is equal to 3x squared plus 2x. When we're finding values of a function, basically we can plug anything we want in for that input x. So if we say f of 5, we replace the x with a 5, that's saying take that function f of x and replace x with 5. So we have 3 times 5 squared plus 2 times 5. 3 times 5 squared is 75, 2 times 5 is 10, 75 plus 10 is 85. So f of 5 is equal to 85. It's just substituting that 5 in for x. Or I could do f of negative x. I could substitute negative x in, which means anywhere I have x in the function, I'm going to put a negative x. So 3 times negative x squared plus 2 times negative x. If we square a negative, it becomes positive, so we end up with 3x squared minus 2x. Well, what if I put an expression in there, like x minus 3? Still the same thing. I'm going to substitute x minus 3 anywhere there's an x in the function. So I have 3 times x minus 3 squared plus 2 times x minus 3. And then I'm going to multiply and simplify this and go through the processes until I come out with 3x squared minus 16x plus 21. There are both implicit forms of functions and explicit forms of functions. Implicit forms of functions are where it's defined by an equation in x and y. It's implied that it's a function, meaning it's showing two variables, in this case, x and y. But it's not necessarily saying what one of them is equal to. So 3x squared minus 5y is equal to 7. It has two variables involved, but it's not written in a way to show that one variable is specifically a function of the other. Whereas an explicit function explicitly state it can be written in the form y equals f of x. So it tells you specifically that one of the variables is equal to a function of the other variable, such as y is equal to 2x cubed plus 5x. So y is written in terms of x. Now the difference quotient of a function f at x is given by f of x plus h minus f of x over h, where h is not equal to 0. The difference quotient is basically saying, let's find the difference between 2 points on the function. F of x is the output of the function. X is the input. So if we were to choose 2 points on a function, 2 input values, with a difference of h between them, so if we have 1 point on the function where x is equal to some value, and then we add some value h to that, then we have a second point on the function where x is equal to that x plus h, and we find the outputs of that by plugging in those 2 values, then we end up with a set of 2 inputs with 2 related outputs. And the difference quotient is basically finding the difference of the outputs over the difference of the inputs. In this case, we've said the difference of the inputs is h. We moved x by h. Now, obviously, h cannot be equal to 0 because we're dividing by h, and if it was 0, we would be undefined. This difference quotient is used to define the derivative. We will not cover derivatives in pre-calculus, but when you get into calculus, this is the basis of derivatives, the difference between the outputs over the difference between the inputs. You must simplify the expression in order to cancel the h in the denominator. So no matter what function you're dealing with, you go through the simplification of the difference quotient and the h in the denominator will cancel out. If it does not, you made a mistake. So let's do an example. What if f of x is equal to 3 over x? Well, then to use the difference quotient, I need to find f of x plus h. So we're going to substitute x plus h in place of x. So we get 3 over x plus h. Now the difference quotient is f of x plus h minus f of x over h. So we have 3 over x plus h minus 3 over x over h. We want to combine that numerator and simplify it. So to do that, we look for a common denominator, which turns out to be x times x plus h. We then combine the first rational expression with the second rational expression, and we end up simplifying it down to negative 3h over x squared plus hx all over h. And we can see that we can now cancel that h in the denominator with the h in the numerator, and we end up with negative 3 over x squared plus hx. So realize that even though we cancel out that h, there may still be h's in our final difference quotient, but that 1 in the denominator will always cancel out. What if f of x is equal to 3x squared minus 2? Well, then again, we need f of x plus h, so we get 3x plus h squared minus 2. The difference quotient, we're going to take that f of x plus h and subtract f of x, divide it by h, so we get 3x plus h squared minus 2 minus 3x squared minus 2. Please be careful when you do this. When you subtract f of x, make sure you put parentheses around that expression so that you don't make any mistakes along the way, and that'll help to make sure that we distribute that negative sign through, giving us negative 3x squared plus 2 in the numerator. Go through and simplify that numerator until we get down to 6hx plus 3h squared over h. And then as you can see, we can eliminate the h in the denominator. So we divide the numerator and denominator by h, and we get 6x plus 3h. Well, how do we find the domain of a function? Well, we start with the domain as the set of all real numbers. So that's our starting point. We always assume the domain is the set of all real numbers. Then we look at if the equation has a denominator, exclude any numbers that give a 0 denominator, because obviously we cannot divide by 0. Dividing by 0, the answer is undefined, or the result is undefined. So obviously you cannot have a function whose input has a denominator being equal to 0 because you can't get an output. And if the equation has a radical of even index, square root, fourth root, sixth root, exclude any numbers that cause the expression inside the radical to be negative, because you can't take the radical of a negative number, or if you have an even index for that, you can't do that without going into imaginary numbers. And we said that we're going to assume that it's a set of real numbers. So we can't allow the expression inside the radical to be negative. So let's try a couple here. If we have f of x is equal to 3x minus 7 over 2x plus 5, and we want to find the domain of this function, we see that we have a denominator with a variable in it. Therefore, we cannot allow that denominator to be equal to 0. So 2x5 cannot be equal to 0. So let's find out what x value causes that to happen. So we set 2x plus 5 equal to 0. We subtract 5 from both sides, divide both sides by 2, and we end up with x equal to negative 2.5. So we know that the domain of this function is going to be all real numbers, but we can't allow it to be equal to negative 2.5. Therefore, the domain is x such that x is a real number and x is not equal to negative 2.5. G of x is equal to the square root of 7 minus x. Notice that I changed from the function being called f to be called g. That's fine. We can call it whatever we want, and many times we will call it something that relates to what we think it's doing. When we don't have something specific that it's a function of, then many times we start with f of x, g of x, h of x, and we start in those letters for naming it. But it could be anything. It could be alpha of x. It could be z of x. And the input variable could be whatever we want to call it too. So we have g of x is equal to the square root of 7 minus x. Now we remember that we cannot take the square root of a negative number. Therefore, 7 minus x has to be greater than or equal to 0. So we want to find out what values of x will allow that to happen. So we subtract 7 from both sides, and we have negative x is greater than or equal to negative 7. Then we want to divide both sides by negative 1, so we get x by itself. And remember, when you're dealing with inequalities, if you multiply or divide by a negative number, then you have to change the direction of the inequality. So x less than or equal to 7. So therefore, the domain is all x such that x is a real number and x is less than or equal to 7. And we can see by looking at this, if we were to make x greater than 7, so say 8, 7 minus 8 is negative 1. We can't take the square root of negative 1. If we made it equal to 7, 7 minus 7 is 0. The square root of 0 is 0, so that's allowed. If we made it 6, 7 minus 6 is 1. The square root of 1 is 1, so we're fine. When are functions defined? F is defined at x, or f of x exists if x is in the domain of a function f. What that's saying is, if your input is in the domain of the function, then there will be an output f of x. F is not defined at x, or f of x does not exist if x is not in the domain of a function f. So that's saying if x is not in your domain, then there will be no output f of x associated with it. Now let's find the domain of an application. Right? Look at something in the real world. Keeping it simple, express the area of a square as a function of the length of a side. Find the domain. So we're just going to let x be the length of a side of the square. Now we should know that the area of a square is equal to the length of a side squared. So I'm going to say a of x, a for area, is equal to x squared. So now I have the area of a square as a function of the length of the side being x. So now let's find the domain. If I want to find the domain, I look and I say, well, what values can you plug into x and have it work? Remember, we start with the set of all real numbers. And x squared, I can plug any real number into x squared and get a result. Negative 7 squared is 49. 2 squared, 4. 0 squared, 0. So it works for all of those. But we have to take into account the application. In this case, x is defined as the length of a side of the square. The length of the side of a square cannot be negative, and it can't be 0. If it's 0, you don't have a square. So because of that qualification that this is the length of a side of a square, the domain is all x such that x is a real number and x is greater than 0. So basically that x is a positive real number. Now let's get into some operations on functions. The sum of f plus g. If f and g are functions, the sum of f plus g is the function defined by f plus g of x is equal to f of x plus g of x. So essentially, you're adding the two functions together. The domain of f plus g of x is the intersection of the domain of f of x and the domain of g of x. Basically, if there is any restriction on the domain of f of x or any restriction on the domain of g of x, when you add those two functions together, those restrictions have to be part of that sum of the functions. Let's look at an example. Find f plus g of x if f of x is equal to 3x squared minus x and g of x is equal to negative x plus 5. F plus g of x is equal to 3x squared minus x plus negative x plus 5. Again, as I said in a previous example with the difference quotient, make sure that you put parentheses around that second function just to make sure that you carry things through properly. And now we just simplify that expression by adding the terms, and we get f plus g of x is equal to 3x squared minus 2x plus 5. Now to find the domain, we look at f of x and g of x, and we see there are no restrictions on either of those domains. Therefore, the domain of f plus g of x is all real numbers. For the difference of f minus g, if f and g are functions, the difference f minus g is the function defined by f minus g of x is equal to f of x minus g of x. And again, the domain is the intersection of the domains of f of x and the domain of g of x. Any restrictions on the domain of f of x or the domain of g of x must carry over to the difference. Find f minus g of x if f of x is equal to 3x squared minus x, and g of x is equal to negative x plus 5. Again, we're just taking the difference of, so f minus g of x is equal to 3x squared minus x minus, remember the parentheses, negative x plus 5. Simplify the expression until we get f minus g of x is equal to 3x squared minus 5. For the domain, no restrictions on the domain of f of x or g of x. Therefore, the domain of the difference of f of g, f minus g of x, is the set of all real numbers. The product, f times g. If f and g are functions, the product f times g is the function defined by f times g of x is equal to f of x times g of x. And yet again, the domain is the intersection of the domains of f of x and g of x, so any restrictions on either one of those sets becomes a restriction on the product. Find f times g of x, and notice I didn't put the dot between f and g in this. So it's just f times g of x. You don't need to put that dot there. F times g of x is fine. If f of x is equal to 3x squared minus x and g of x is equal to negative x plus 5, so f times g of x is equal to 3x squared minus x times negative x plus 5. We multiply through, simplify, we get f times g of x is equal to negative 3x cubed plus 16x squared minus 5x. And again, no restrictions on either domain. Therefore, the domain of the product is all real numbers. Quotient, f divided by g. If f and g are functions, the quotient f divided by g is the function defined by f divided by g of x is equal to f of x over g of x, where g of x is not equal to 0. Remember, we can't divide by 0. So what this does is this adds a restriction onto our domain of the quotient that it's the intersection of the domains of f of x and g of x, but also we can't allow g of x to be equal to 0. So if we have the f divided by g of x, if f of x is equal to 3x squared minus x and g of x is equal to negative x plus 5, then we have f divided by g of x is equal to 3x squared minus x over negative x plus 5. We cannot simplify that any further, so that's fine as it is. We know there are no restrictions on f of x and no restrictions on g of x other than the fact that we cannot allow the denominator of this to be equal to 0, so we can't allow g of x to be equal to 0. So we can't allow x to be equal to 5. So therefore, the domain is all real numbers such that x is not equal to 5.